This continues the unit on the quadratic formula. We had done a bunch of problems solving by the quadratic formula, and this is sort of a subset of that, and then we'll get into some non-real solutions to quadratics as well. When you write out the quadratic formula, x equals opposite b plus minus the square root of b squared minus 4ac all over 2a, what's under the radical plays an important part in what types of solutions you get. And we have a special name for that thing that's under the radical. Okay, that part that's the b squared minus 4ac, not including the radical, just the b squared minus 4ac. We call that the discriminant. Discriminant, yes, it comes from the word discriminate, but it means it's allowed us to tell the difference between the different types of solutions. So b squared minus 4ac is the discriminant. Now let's think about what that discriminant does. If that discriminant is negative, that b squared minus 4ac is going to be less than 0, we're going to end up with non-real solutions. If that discriminant is a perfect square, then the radical goes away completely. We have no more square root in our answer. Everything is an integer top and bottom, which must mean we get rational numbers. Things like 2, -3, even 7/8, that's a rational number. So if you look at the little chart down the bottom that I made, if the discriminant is positive and a perfect square, we get two rational numbers. Positive but not a perfect square. So let's say the discriminant was 7. Then our formula is going to have a square root of 7 in it somewhere. It's a real number. It's just not rational. So we'll get two irrational numbers. We saw an example in the last video where that b squared minus 4ac part came out to be 0. Well, if that discriminant is 0, then the only thing that's left is the negative b over 2a. And then, of course, if it's negative, we'll end up with non-real numbers. And so the first two cases, right, positive being either a perfect square or not a perfect square, that means it's going to cross the axis twice. Where? Well, I don't know. Maybe it crosses it here and here. Maybe it's upside down and it crosses it at two places. If the discriminant is 0, we're going to end up with something like this, where it hits the axis once, or maybe something like this, where it hits the axis once. If the discriminant is negative, you're going to end up with one of those cases where the parabola is up here somewhere, and it just never crosses the axis. So when you get two non-real numbers, those values are saying it doesn't cross the x-axis at all, because those values that you get when you solve the quadratic are the places where the graph crosses the x-axis. Well, if your answers are not real, then there's no place where the graph crosses the axis. All right, take a look at this one. It says use the discriminant to determine the number of solutions and solve using the quadratic formula. First thing, if we're going to solve with the discriminant, we got to take that 3 over to the other side. So negative 2x squared plus 5x minus 3 equals 0. So a is negative 2, b is 5, c is negative 3. So the discriminant is the b squared minus 4ac part. It's 5 squared minus 4 times negative 2 times negative 3. So the discriminant equals 25 now. Minus, minus, minus. Two negatives make a positive. Positive times a negative is a negative. 4 times 2 is 8 times 3 is 24. So the discriminant is 1. What does that tell us? Well, first of all, it's a positive number, so we're not going to get non-real solutions. What does that 1 fit? Well, 1 is not 0, so it can't fit the 0, can't fit the negative. It must be one of these two. It's positive. Is 1 a perfect square? Yes. So we're going to end up with two rational numbers. Okay, our solution is going to be two rational numbers. What are those rational numbers? Well, we don't know what the rational numbers are till we solve with the quadratic formula. Now, here's the good news. Half the quadratic formula is already done. Because remember, the quadratic formula is x equals the opposite of b plus minus the square root of b squared minus 4ac. We already figured out that b squared minus 4ac was 1. So that discriminant part is half the solution of the equation. And then over 2a. So 2 times negative 2, negative 4. So yes, I know the square root of 1 is 1. I just put that there to make a point. So I get negative 5 plus minus 1 over negative 4. So option number 1, x equals negative 5 plus 1 over negative 4. Option 2, x equals negative 5 minus 1 over negative 4. So negative 5 plus 1 is negative 4. Negative 4 over negative 4 is 1. Over here, negative 5 minus 1 is negative 6. Negative 6 over negative 4 is positive 3/2. So those are my two solutions. X equals 1, x equals 3/2. So this parabola is pretty narrow. If they cross in the x-axis at 1 and 1.5, those are pretty close to each other. So once we calculate the discriminant, we get some idea as to what types of answers we get. Then the quadratic formula is half solved or more than half solved. And you notice that I got two answers, and they were both rational numbers. 1 is a rational number. 3/2 is a rational number, because I can write each one as a fraction where both numerator and denominator are integers. All right, this question has a little bit of a hint to it. Right? It says solve 3x squared minus 7x plus 5 equals 0. Write your answer in standard form a plus bi. So this tells me right away I'm going to get some type of negative number under the radical. Let's see what it is. My a value is 3. My b value is negative 7. My c value is 5. So he said the discriminant was b squared minus 4 times a times c. Negative 7 squared is 49. 4 times 3 is 12 times 5 is 60. Okay, so like we suspected, we were going to get a negative number for that discriminant, which means we're going to get two non-real answers. What are those two non-real answers? Let's find out. Remember the formula, x equals the opposite of b plus minus the square root of the discriminant, which is negative 11, all over 2 times 3, which is 6. I can break this up into two parts. I can write it as 7 over 6 plus minus the square root of negative 11 over 6. And that square root of negative 11, 11's not a number that I can simplify. In fact, it's a prime number. So I can write that as I times the square root of 11. But watch how I'm going to write my final answer. 7 over 6 plus the square root of 11 over 6 times I. Because it says write it in the form of a plus bi. So in the form of a plus bi, that's my a, that's my b, that's my I. So I'm moving those things around so that I can put a number plus minus a number times I, and that's how I do it. Okay, if it was possible to simplify the square root of negative 11, I would. Best I can do is pull out that imaginary unit times the square root of 11. All right, let's look at a couple more in slightly different contexts. Look at this one. If I'm asked to solve this equation, I'm going to do two things. One of them is I got to bring that 2x over to the other side. Right? So that 2x is sitting on the right side. Let me bring it over to the left side. So let me write it as negative 2x squared over 5 plus 2x minus 3 equals 0. Is it possible to solve this the way it is? Absolutely. A is negative 2/5, b is 2, c is negative 3. If I want to get rid of that fraction, if I would rather work only with whole numbers initially, multiply both sides by 5. Now clearly 0 times 5 is still 0. Over here then, I'll end up with a negative 2x squared. 5 times 2 is 10. 5 times 3 is 15. Now I've got it in what I'm considering an easier form. So my a is negative 2. My b is 10. My c is negative 15. My reminder is make sure that you're multiplying everything through by 5, not just the term with the fraction. All right, so if I want to set up my quadratic formula, x equals the opposite of b plus minus the square root of b squared, so 10 squared is 100, minus 4 times negative 2 times negative 15, all over 2 times negative 2. Right, let's work through that discriminant and simplify. negative 10 plus minus the square root of 100 minus 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 makes a minus. 15 times 2 is 30. 30 times 4 is 120. So I get x equals negative 10 plus minus the square root of negative 20 all over negative 4. Now, what can I do with that square root of negative 20? Looks like it's got a perfect square factor in it somewhere. In fact, it does. So let's write that square root of negative 20 as square root of negative 4 square root of 5. And then the square root of negative 4 is 2i. Sometimes we write it like that. But how about this time writing it like this? 2 square root of 5 times I. So that when I come down to my next step, I can start simplifying this. So I can write it as x equals negative 10 over negative 4 plus minus 2 square root of 5 over negative 4 times I. And then my last step down the bottom, I can fit it in, is to simplify those individual fractions. So negative 10 over negative 4 simplifies to 5 halves. So I get 5 halves plus or minus, and I can knock a 2 out of top and bottom here. So I get a square root of 5 over negative 2 times I. All right. Let's just make sure you see where I got those 2's from. I took a 2 out of the top. 2 divided by 2 is 1. Negative 4 divided by 2 is negative 2. So I got just a square root of 5 on the top, and I got a negative 2 on the bottom. And there it is, a plus bi form. Right, what do these answers look like when I work through completing the square? So let's try one by completing the square. This is not in the form yet of being ready to complete the square, so let's distribute the x. X squared minus 4x equals negative 5. Now that looks like a completing the square problem. We said it's half of b, square it, add it to both sides. So how does this work? Half of negative 4 is negative 2. Square negative 2, and I get 4. So what I'm going to have to do is add a 4 to both sides. Let's see what that looks like. So add a 4 to this side. Add a 4 to that side. And I get x squared minus 4x plus 4 equals negative 1. What's on the left side factors as a perfect square. It's going to be x minus 2 squared. Foil it back if you don't believe it. X squared minus 4x plus 4. You can see right away we're not going to get real solutions because I've got something squared equals negative 1. Well, still we take the square root of both sides. We put our little plus minus here. And so I get x minus 2 equals, on the other side, the square root of negative 1 is just I. And now add a 2 to both sides and we're done. X equals 2 plus minus I. And so completing the square works even if the answers are not real. And this is how it looks. If that was a negative 4 on the other side, I'd end up with 2i. If it was irrational, I could still end up with, an I squared of 3 or something like that. But that's what it looks like by completing the square. And you'll see right away that you end up with non-real answers because you'll get something squared equals a negative number. But that's all right. Keep going and see what the non-real solutions are. All right, one more example here. Let's do a little word problem. So this goes back in ancient history. At one time, there was such a thing as a compact disc, and we listened to music on CDs. 1989 to 2009, global music sales of physical CDs and tapes in billions of dollars was given by this S of X formula. S for sales. X is the number of years after 1989. So X equals 1 would be 1990, right? Number of years after 1989. It also says the values were given in billions of dollars. So the question says, when were sales equal to $12 billion? Yeah, all right. I should replace this value here with a 12. It's a quadratic formula. I can see that there's a negative before the x squared, so it's actually a parabola that opens downward. Let's see what we can do with this. First thing is, let's subtract the 12 from both sides. So I get 0 equals negative 0.095, right? Don't lose that 0 because there's a 0 before the 95. So negative 0.095x squared plus 1.585x. If I subtract the 12 from both sides, I get a minus 6. Right, so my a value is negative 0.095. My b value is 1.85. My c value is negative 6. All right, let's work our way through the quadratic formula. X equals the opposite of b, so negative 1.85, plus minus the square root of b squared, minus 4 times negative 0.095 times negative 6. All over 2 times negative 0.095. All right, let's work our way through what's under that radical. Let's take 1.85 and square it. Follow along and see if you get the same answer I do, even if you have to pause this for just a second. And then we're going to subtract negative 4 times negative 0.095 times negative 6. All right, so to save a little bit of space, I'm going to kind of work through this on the side and then come back. So underneath this radical here, I got 1.1425, and now I need to take the square root of that. Right, so I get x equals negative 1.85 plus minus, when I take the square root, 1.1425. I get 1.07. Right, I'll keep the same number of decimal places as I have in the first part. So 1.07. And then on the bottom, I get 0.19. Actually, negative 0.19. Now, this is going to be a case where I get two answers. Are they both useful answers? I don't know. Let's figure this out carefully. So up on the top, I'm going to carry through my two different versions. One possibility is that x equals negative 1.85 plus 1.07 over negative 0.19. The other possibility is that x equals negative 1.85 minus 1.07 over negative 0.19. All right, let's calculate each of them and then see if those questions make sense. I'll run through and do the calculations, you follow along, and let's see if our numbers match. All right, so I ran through this and I got 4.11 and I get 15.37. So in previous problems, we had done these types of application problems, and we always got one negative and one positive, and we said, well, discount the negative, keep the positive, especially if we're talking about time. But here we got two positive answers. First of all, let's think about what these mean in the context of the problem. It says x is the number of years after 1989. So roughly, if I add 4 years to 1989, I get 1993. What happens if I add 15 years to 1989? I should get 2004. How does this work? I came up with two different years. Well, let's think about how CD and tape sales went. Right? For a while, they were increasing. 1989, increasing. I'll bet you at some point, digital music started taking over, and those sales started decreasing. And so by 2004, they were starting to decrease again. I've got a graph for this. Let's take a look at this graph. I already put the equation in there, and we can look to see what might make sense. So let's orientate ourselves. This is year 0, 5, 10, 15, and 20. So this is 1989. This is 1999. That over there is 2009. We were looking for two intersection points. We were looking for y equals 12. Look at the two intersection points. One of them is right here, 4.11. The other is here at 15.36. What happens is we caught one on the way up, and then we caught another one on the way down. So according to this model, the CD and tape sales actually peaked close to 2000. What is this? 10s of 1999. All right. So about 1999, music sales peaked, and then they started decreasing, and you could correlate that very quickly with the rise of digital music and digital storage systems. And so fewer and fewer people were buying physical tapes had been phased out by them, but CDs as digital music sales increase. So I want to do at least one problem where you see that in this context, it very much makes sense for that graph to intersect that point twice. And that wraps this video up.